So let's talk a little bit more about why you should pick Gemma 3 versus Gemma 2. Our previous video was about how to actually deploy Gemma 3 using a Docker image. It was very practical, code-based. Now we're going to get into a little bit of the theory. One of the things we touched on in that last video was that the context size went from 8,000 to 128,000 tokens. Why didn't Gemma 2 have a bigger context size? Well, in these older models, and Gemma 2 is not old by any stretch of the imagination, but in these older models, you are going to run into some complications when you try to deal with context windows. For basics, context windows, compute complexity scales quadratically. For any of you want big O notation, O to the n squared. As you increase the context size, every prompt that you run is going to have to go back through that old context, and it's going to cost you a lot. Keep in mind that when you enter in these large context windows, everything is still being stored as vector embeddings. In the older models like Gemma 2, you were using fixed positional vector embeddings. When you use fixed positions, as you get longer and deeper into the history chain, the chain of history of your context window, the model has a more and more difficult time of determining prioritization. Which one should I stick with? Which one should I use now? So to keep it fresh and to give it some sort of prioritization, you have to include something called rope. Now, rope is not a new concept. It's been around for a little while, but it's something that Google just introduced into the Gemma 3 model versus Gemma 2, and it's one of the main reasons why Gemma 3 is able to handle the large context window. Now, let's talk about rope. Okay, so what is rope? Well, rope is rotary position embeddings. And if you think about it, why didn't Gemma 2 just have this giant context size? It's because as you increase the context window, the compute complexity increases quadratically. Every time that you add a new token into a context, it's getting processed into a vector embedding. Traditionally, the vector embeddings were fixed position, and you can imagine that as you get more and more and more context and the context becomes more varied, the distance between each of those vectors is going to grow. And as it grows, the models are going to lose their ability to connect these pieces together. Remember, this is still a transformer architecture. If you guys remember the paper, attention is all you need. Kind of goes back to that point. Transformers, they don't have this concept that each token has a positional value, like in word order. You have to provide that to them through the vector embeddings. And if your vector embeddings start getting more scrambled and further away and harder to process, you're going to lose quality in your model. So it's not as simple as just increase the context window. A, it's compute. B, it just doesn't work. So what does rope do to solve this problem? Rope adds in a rotation matrix. And what that means is instead of just adding another vector in, this provides new positional information that's encoded into it. So it rotates the token based on its original position and gives it, well, this is based on sine and cosine, and it's going to give it a new rotation proportional to its original position to ensure that relative positions between tokens are encoded in their dot products embeddings. Yeah, I just read that part, but you kind of get the idea here. You don't want to have this very disjointed sparse graph where when your model encounters a new token, it has to go and try and process and make decisions. You want to make those decisions as quick and easy as possible, and that's what rope's providing. So this is where some of the magic of Gemma happened. To go from Gemma 2 to Gemma 3, one of the major changes that Google made is they had to introduce quite a bit of changes to rope itself, which means that that sine and cosine function, they each have their own frequency, and that's a meta parameter that they had to go and tune, and that's how they were able to increase the context size. So you couldn't just naively do it, otherwise you're going to get what they described in their paper as essentially static. So if you think about the analogy they used is if you have a radio station, you try listening to it from the other room, that's what it looks like, and the more context you add, the further away you get from the radio. By doing this rotation in a refined rope, where they fine-tuned those sine and cosine parameters to determine the rotation distance, that's where they were able to basically clean up the signal and find the right frequencies for it. The other thing they did is they changed the scaling factor, so it's another fine-tuning. The scaling factor here just means rotation angle. So if you allow the rotations to become too extreme, you can lead to instability over longer times in your model. But yeah, that's the basics of what they did. Okay, and the next innovation. This one's a little bit simpler than rope. There's no sine and cosine. This is just, okay, for starters, what is a context window? A context window is essentially a key value pair that you're storing in the VRAM of your GPU. When I take that context window and I make it 128K instead of 8K, what am I doing? I am massively increasing the memory and computational resource consumption of my model. So how do I fix that? Well, you do what Google did. Instead of taking the entire window, context window, and loading it in at once to then be searched through and maintained, they put a windowing function on top of it, which just means when I go to do a lookup, don't take the entire window, take windows, load them into memory, and then shift across it over time until you find the answer that you're looking for, and then return the answer. The way they did it is actually, it's interleaving windows. It's a little bit more complex than the way I'm describing it. I couldn't find the algorithm online. Maybe it's available somewhere, but I couldn't find the exact definition of how they did it. But this, you guys kind of get the point. It's pretty straightforward. Reading this KV store in a windowed fashion to continuously load and unload. So that's the KV innovation. All right, let's talk about a few more of the technical pieces. I'm going to go through this list here. So we have three main strategies that Gemma 3 used to improve their scaling to go from an 8K window up to a 128K window. So let's go through them one by one. We have the key value cache optimizations for Gemma 3. We have the improved efficient scaling strategies in Gemma 3, and we have rope that we previously talked about. So let's go from the top. So what key value cache optimizations do we make here? We have sliding window interleave detention. What that basically means is instead of having one large context window, you break it up. Think of it like if we have 128K, we break it up into 4 equal sections of 32K. Then we have smaller overlapping windows between 1 and 2, 2 and 3, 3 and 4. And then those things are going to handle all of our context. Second, we have quantization and memory compression. Anybody that's worked in these models should understand this out of the box. If you get a float 32, you want to reduce the size of the memory footprint, just reduce it down to 8 bits. That's what they did here with the context. It says reduce memory usage without significant loss of accuracy, but I'm sure that Google made sure that that was true. Third one, selective key value cache storing only the most important key value pairs. What does that really mean? It means within each of those smaller context windows, you have key values, and then you need to determine which ones have the highest attention ranking. And so then you can choose to selectively store those and then direct the cache to there. So that reduces the cache size and improves efficiency. So then paging, says similar to the way that things work on operating systems. This way, in a classic paging setup, that's the way you're going to access memory from fastest to slowest. Here, they would do the same thing. Okay. All right. Now, efficient scaling strategies. This is another way that we can go up to 128K. So anyone out there that's thinking about training their own model, you should consider these same problems and solutions that Google went with. So number one, they pre-trained on shorter sequence lengths. Okay, fine, not a big deal. Second, they then scaled up to 128K context in final stages. They didn't start with 128K. So we talked about how there's this O(n) squared type quadratic cost. So if you can train on smaller lengths and get the same results, you're going to want to do that. So then, okay. Then we have resource savings. They minimized overall training compute, accelerated development timelines, and enabled. This is consultant speak. They cut corners where they could, just like everybody else does. Okay, and then the final one we already talked about rope for a little while, but here we have number one, base frequency adjustments, so fine tuning the rotation frequency. We already discussed that for a little bit, where you have a couple variables that you can play with to kind of, if you think about it with that radio analogy, to dial in the signal to make it clearer or fuzzier. Maintaining positional accuracy over long distances. That's the whole point of rope. Kind of the same deal here. So if originally you had, just take it into 3 dimensions, if you had vectors and they start going in other directions and the vectors become really far apart, then you can apply sine and cosine so that your functions are limited and they'll rotate back around so that you don't lose, the vectors don't get too far apart, that they'll never be prioritized again. Okay, then we have scaling factor implementation. We talked about some of this too, where you're going to scale down or scale up the rotation factors to try and bring them back around more quickly, and then you need to control that, otherwise you can get scaling factors that are just circling through, rotating way too quickly. So you want to have these things kind of smooth out. This is all part of the fine-tuning process. If you want to do this yourself, you're going to need a very robust system of model analysis, intermediate checkpoints. You're going to have to go through the whole process. This is just a summarization of what probably took somebody, a team of people, months of work to do. Okay, and then you have optimized for 120K context. Yes, you're going to want to optimize everything for the context size that you have. But by doing these 3 major things here, key value cache optimization, scaling, using scaling when you're doing your training and pre-training, and then finally doing rotary positional embeddings, so your vector embeddings don't get too out of whack. They're able to increase the context size. So that answers that question. If you want to know why didn't they do it from the beginning in Gemma 2, well, they weren't able to do it without these optimizations they put in for Gemma 3. Okay, and then as a bit of an outro here, so what have we learned today? We did a deep dive on exactly how they actually made the updates to the context window. Most of it, as we saw, was around rope and key value updates. There was some training magic that went on in the background. There were some optimizations. There were some corners cut. You should have a general idea, though, if you were going into this at the high level. Now, this is a technical deep dive, but really what that was covering the the large bullet points of, like, if I was going to open up a slide deck and say these are the 4 things or 3 things that I need to do to increase the context size of this model that I'm training, that's kind of the level that we're at here. If you guys are interested in doing a deeper dive into exactly how to do these exact things, like how do we actually do implement the sliding windows on these key value context, on these context windows, we can talk about that. If you're interested in getting deeper into like the pagination techniques they're using, we can get deeper into that. But then there's a few things that we didn't cover in exactly what the updates were from Gemma 2 to Gemma 3. So we didn't really get into the multimodality or the multilingual pieces of it. To me, that's slightly less interesting than the context window. It's more specific to this use case. Most people are not going to be out there building multilingual or multimodal models, especially if you're going to use this as a base. You've already got a pretty good starting point. So in addition to that, we also have the secret sauce, right? What was Google's secret sauce? And really, it was just extremely curated, high quality data with really, really good scientists backing it up to do all the fine tuning with a very robust model testing process. And that's not really secret sauce, that's everybody's trick. So this is very approachable. You guys can do this, you can use it. If you want to take these kind of lessons and then apply them to your own model, go for it. And then, of course, please leave a comment. If you guys have any questions, like, subscribe, send me a message if privately if you're not comfortable making comments, and we can talk more about it.